I think I covered this in the last class, but I made one mistake and I have one additional comment about something. So I came back to here. And mistake was there. Mistake was here. This one. This one. No. This one. I'm sorry. This one. Okay. So when calculating this value, which is the output impedance peak value, this part, this is the output impedance, closed output impedance, simplified one. So this is very close to our previous example. So we are just seeing this, and we are evaluating magnitude of this at this frequency. Then denominator is omega g1, not omega g1. It should be omega m. Okay, omega m. That was a mistake. So now I'm fixing this. Okay. Sometimes I make some minor mistake. So I hope you student you can catch it. Right? Some simple mistake like this. Omega m there. And one important comment here. Right. So this slide shows the waveform of step load response is this one. Step load response this one. And this time constant is determined by this number. This tau is 1 over this frequency was this frequency was omega g2. So 1 over omega g2 is time constant of this. Okay, so this is fast, very fast, right? Because omega g2 occurs at high frequency. Omega g2 is somewhere here, and omega g1 was somewhere here. Okay. So if you remember the previous lecture, this omega g1 determines speed of step impulse response. Okay, and omega g2 determines speed of step load response. So this step load response is inherently faster than step impedance because of the location of this. Okay, that is the first comment about this. So faster response is due to this characteristic behavior of this thing. Okay, let me go back. So the loop gain is something like this. This is the omega g1. This is omega g2. This is omega naught, power state double pole. This is the omega p2, and omega p1 is at the omega ESR. They cancel. So you are not seeing this, okay? Because the frequency of this one is much smaller than this. Okay, so this step load response is inherently faster than step impulse response. That's obvious. There is another way of understanding this, which is more desirable. So think about the circuit diagram of this converter. Assume this is buck converter. This is buck converter actually. Then circuit diagram of buck converter is this one. The switch, diode, and L, and capacitor, and load resistor, and this load disturbance coming in here, and the step disturbance is coming in here. Okay? And you have feedback controller, of course. We are talking about this closed loop system, voltage mode control. Okay? Then disturbance is here. This is very fast. This disturbance directly affects this. They are very close, right? It does not, maybe it will pass through this, but it is directly connected. They are in the neighborhood. So this response to this disturbance is very fast, right? And this disturbance is coming in the input. So there is just some component here, inductor, capacitor, which is very large, relatively large. So there is just some delay, okay? Response to this step change will be slower. then response to this one, because this is directly connected to our voltage and this is remotely connected to the our voltage. Okay, so this reason and this reason, the step load response should be much faster than step input response for any converters. This is true for any converters. Okay, right? Okay, and this is the last lecture, next topic about this voltage mode control. Okay, we found out this column, the voltage mode control is very good, almost optimal, and ideally suited for the buck converter. So with voltage mode control, you can control everything about the buck converter. Okay, but there is one problem, maybe two main problems with the voltage mode control. But first one is this. How about the boost and the buck boost converter cases? Okay. You may expect some similar thing will happen to these two converters. This is not true. You cannot use this voltage mode control for this converter. You can use, but the performance will be very poor. Okay, will be very miserable. Right. And during these discussions of voltage mode control, we used a converter example in the CCM. Okay. Implicitly, we are assuming CCM operation, but all the converters will move CCM to the DCM when the load current is decreased. Okay, so what about the DCM operation? What will happen in the DCM operation, and what will happen if transition between CCM and the DCM operation? Okay, that is the big question, right? So I'll give you answer to that, to these two questions. Okay. So, first, case of boost and buck boost converter. What's special about these two converters? And these two converters has RHP0 in duty ratio to output transfer function. Right? It's called non-minimum phase system, and I discussed all the details about this non-minimum phase system. Okay, maybe this one. In the previous lecture, in this semester, non-lecture topic. Okay. 9-1, lecture 3. We discussed all the details about this non-minimum phase system using boost converter example. Boost converter example. Okay. All the converters except buck converter and buck derived converter, all of PWM converter, they are non-minimum phase system. It has RHP0. Okay. Why they have RHP0? We went through all the details about that, and the conclusion of that, converter whose load current is supported by the uptime diode current should have RHP0. Okay, let me give you two examples. Okay, this is the circuit diagram of boost converter. So boost converter, you have inductor here and the switch and diode, and this is output stage. This is a boost converter. Okay, then load current is this one. All right, so this is R. Okay, load current. The average value of this capacitor current must be 0. Okay, otherwise it will reach very high voltage and capacitor will be break down. All right. Okay, so this is the average value of this is 0. Then this IO, which this value is average value of the diode current. Okay, that is the meaning of supported by off-time diode current. During the on-time, inductor current is switch current, and during off-time, this diode current, inductor current is diode current. So we call it off-time diode current. This is true, and this is buck boost converter. Is shown here. Same is true. Okay, this ID and this ID, this is polarity is reversed. Okay, so IO is here. So here IO is supported by uptime diode current. So for this converter, it must have RHP0 in only duty ratio to output transfer function. Buck boost converter. Okay, that means other than buck converter, you have this RHP0 system becomes non-minimum phase system. At that case, this voltage mode control is forbidden, cannot be used. Okay, let me explain that here. Okay, maybe I can cover one or two pages. Okay, so this is the example of boost converter or buck boost converter. They are basically the same. Okay, this is the loop gain, and this is the control to output transfer function of these two converters. And control to output transfer function is simply this duty ratio output transfer function times modulator gain FM. So this equation is something like this. Okay, this is the expression for the control to output transfer function. Shape structure is the same as duty ratio to output transfer function. Only difference is we have this constant which is incorporated here. All right. Before this, let's think about the buck converter case. Okay, so this is the buck converter case. I'm using this color. So buck converter case. Maybe this is omega ESR. Okay, buck converter case. Buck converter case is this goes to -2 slope here. So control to output transfer function is something like this. This is a buck converter case, buck case. Let me use big line here. Okay. So it goes like this, and there is no RHP0, so -2 slope goes down to here, and it has the ESR 0, so slope becomes -1. Okay, this is the case of the buck converter. Case, right? And the loop gain crossover frequency is something like this. This will be the same. Assume this part is the same. This part remain the same. It goes -2. -1 slope, and here omega G2 is located here. Okay, omega P1 is located here. So ESR is cancelled. So it goes like this. Okay, and here is another pole omega P2. So this is -2 slope. Okay, -1 slope. Okay, so this is the case of the buck converter. Right. I'll explain buck boost converter later in comparison with this. And let's take a look at the phase. Phase remain the same up to this point. Okay. And the phase go to this. And -1 slope is maintained up to here. And eventually it is -2 slope here. So it goes like this. Okay, this is buck case, right? So at the loop gain crossover frequency, it has large phase margin usually, right? So this is buck case. This is the loop gain characteristic of buck converter, right? This boost or buck boost is different. Okay, so buck boost converter, it has RHP0. Okay, so this is the boost converter case. Boost converter, it has RHP0. And it has omega ESR. So this is the boost case. Okay, boost case will remain the same. and this phase will be something similar to this, but at this frequency, at this omega ESR, you have what? Omega P1, okay? So they canceled, and this -2 slope will be maintained because this is canceled, pole and 0 are canceled, and -2 slope is extending. No. Oh, cancelled, right? Cancelled. Okay. Then this becomes -1, right? Because this at omega RHP, this is 0, so pole is cancelled. So this -2 slope becomes -1 slope, and no. It's confused. Not this one. This is the control to output. Okay. This loop gain. Okay. So loop gain. There is a pole 0 cancellation at here. Right. So omega P1 is located at omega RHP. So in terms of the slope, they cancel pole 0 cancellation, and it will go down to -1 slope. And here, this omega ESR is coming in. This is 0 slope, and this omega P2 brings down to -1 slope. Okay, this is okay, right? This is right. So this is the boost case loop gain. Okay, boost case loop gain. Phase is a problem. Okay, phase is somewhere here, but this phase, this is cancelled. Magnitude is cancelled. Pole 0 cancellation. But in terms of phase, this RFP0 behaves as a pole. Okay, so at this point there will be a 180-degree phase delay. Okay, because the phase will be cancelled if this is the value 0, but this is RFP0, so phase becomes minus. It behaves as a pole. So with this phase will be dropped here, something like this. Okay, and it goes down. This is about -180-degree phase delay, and you have pole and increased, and you have this omega P2. So pole will be something like this with this green curve. Okay, you figure out this later. Okay, it's not difficult to figure this out. All right. So phase is very worse here. Phase is very worse. Okay. So if this corner frequency are not widely separated, then actual phase looks like this. Actual phase is something similar to this. This is actual phase. Oh, not more than that. Actual phase. It goes down. Okay, so the phase becomes very worse at this frequency. Right? So to have some phase margin, crossover frequency should occur somewhere here. Right? You understand this? Okay, it looks complicated, but if you follow this, you can understand this. Okay, then final result of this design is this one. So we have design here. Okay, so we follow the standard 3-pole-2-0 compensation. That is the best structure for this, and I obtained this. Okay, so this is the best I can do. This at this crossover frequency is this one, and the phase margin is 13 degree. If I increase this crossover frequency, it becomes unstable. Okay, so this is very similar to the compensation is this one. The compensation of this voltage feedback compensation, we use this, but actually effective one is this part. Okay, so only the integrator is working at this part. Integrator is working at this part, and this omega G1 is working at here, and these are useless. Okay, they are doing anything because it occurs after loop gain crossover frequency. So this is the best design Okay, for that case. I try to simulate this case using PSIM. Actually, this plot is generated from the PSPICE, frequency domain simulation. I try to use the computational method using PSIM, and PSIM won't work. Okay? It was unstable. It was numerically unstable, right? Because of the this small phase margin, I couldn't get any response from the PSIM. It's just noise is coming out, okay? So that means even though there is a small phase margin, practically converter becomes unstable. So we cannot use voltage mode control for the boost or buck boost converter, okay? Voltage mode control is only adaptable to the buck converter, okay? So this is a story. Okay, this is a continuation of the previous lecture. We are discussing the limitation of voltage mode control for the case of boost and buck boost converter, and we found out that voltage mode control is not comparable with boost and buck boost converter if we apply the voltage mode control to those two converters or any other variation from the boost and the buck boost converter. You can make the converter stable, but closed loop performance will be very poor. Okay? That is the one problem of one limitation of voltage mode control. And another problem is this one. So we are talking about the buck converter employing the voltage mode control, and the converter shows really ideal characteristics on the CCM operation, so you can optimize everything in buck converter case in CCM operation with voltage mode control. But question is, there is another operational mode called DCM operation, and what about the DCM mode operation? Performance of the voltage mode control applied even buck converter can be a problem. And how about the transitions between CCM and DCM operation? This could occur in the digital load case. Okay, so we should understand this. Right? Okay, so we go to this page. We go to this page. Okay, so it's about the. Oh, why it's not going? This page. Okay. So we're going to discuss the performance of buck converter, which employs the voltage mode control. The control scheme is not shown in detail, but consider this is the voltage mode control. Okay. First, I'd like to explain some of the background information. This is a kind of review about the DCM operational mode. So this is a case of buck converter. This is the inductor current waveforms. Okay. Assume this voltage is 10 volt and our voltage is regulated at 5 volt. Okay. That is assumption. That case duty ratio is 0.5. So this is one operational period, and half of that is on time period, and the remaining half is the uptime period. Okay. For the buck converter case, this IO is same as the average value of this inductor current IA, because this voltage entering, leaving, so this capacitor should be balanced at 0. Otherwise, our voltage will increase, so the capacitor will fail. So to avoid that, the circuit somehow they are operating in the manner the average value of this capacitor current is 0 always. Okay. Of course, the AC current can go in and leaving from the capacitor, but average value is always 0. Okay. That means this out current, assume this is a constant, this is a constant, then this is the DC, that value is same as the average value of the IL. Okay. So that is this one, this inductor current, and this average value is load current. Okay, this is average notation. IO, which is VO divided by R, load resistor. Okay, and this our voltage is regulated with this voltage mode control. So this value is fixed, and you are increasing the load resistance R, then the average value of IL or IO, load current, is decreasing. So this will be load, okay? Inductor current will be start here and move to this one, and eventually there will be an instant where this current start from 0 and go to the peak value and come back to the 0 and repeating this, okay? This is the borderline between continuous conduction mode and discontinuous conduction mode. Operation here is called continuous conduction mode operation. Continuous conduction mode means the inductor current is continuously flowing through the inductor. So this current is continuous. Okay. Then this is the critical case, and you further increase this. Okay. If the converter is operating with the same principle, then this current should go down. Okay. Should go down like this. So it starts from here and reach the peak value and becomes negative, and go up. Okay? But this is impossible. Because this is diode current, the uptime inductor current is flowing through diode. So this negative current is impossible because we are using this diode, which is basically unidirectional device. Diode only flows current from anode to cathode. So this is impossible. Then what will happen? Okay. Then this converter is still operating this condition. Okay. So average value of this purple one is this one, IL. Average value same as IO, and this is regulated somehow with this voltage mode control. Then this value is fixed, and this converter is trying to deliver the same current as the previous case without having this negative current. Okay? Then this area, this purple area, and this red area is the same. Then makes sense. That means inductor current is initially increasing and goes to the peak value and decrease with this, and it reaches 0. Then diode is turned on. Then for the remaining operational period, diode remains turned off. Okay? Then average value of this red curve is the same as the average value of this purple area. So that satisfies the requirement. And this is the operational waveform of inductor current during the DCM operation. Okay? This kind of operation is called the DCM. The reason is obvious. So during this period, inductor current is 0, so it becomes discontinuous. Okay? So it's called the DCM operation. So DCM operation waveform is this one. Okay? Then for this, to regulate at our voltage at 5 volt, so D is duty ratio is 0.5. This is 10, this is 5. Okay? For this case, then obviously D becomes smaller. Okay? That means the voltage gain formula in DCM is totally different from that of the CCM. Okay? To maintain the output voltage constant, to regulate our voltage at 5 volt, as is the case of the CCM operation, then duty ratio should be reduced. Okay? So in this case, duty ratio. Okay, let me use this. Duty ratio is smaller than 0.5. Previously, D in this region was 0.5. Okay, in the continuous conduction mode, if this is fixed and output is fixed, D remains the same. Okay, but if the converter goes into DCM, D should be decreased, right? Otherwise, there is just some conflict. Okay. So this is the case. Obviously, D becomes smaller than 0.5. Okay, maybe there's something 1/4. Okay, 0.25 something. In this case, this is not realistic case. You need some calculation, but concept is this one. Okay, so this is called the DCM operation. So even though the output voltage is regulated for the fixed voltage, always this load current can be very small, R can be very large. Okay, for the standby operation or energy saving mode operation with actually very line load condition, converter always move into DCM operation. So you should consider the DCM case. Okay. Okay. This is the buck converter example. So you are using the same feedback compensation. We derived this, we designed this based on the DCM operation. So first, we determined this omega P1 is located at the omega ESR, and the loop gain crossover frequency is selected something between 0.5 to 0.3 of the switching frequency. So I select this strange number, and for these values, I arbitrarily selected R1 with this value, and other values are selected based on the equation you are knowing. Okay, so with this, I compared with the Dewey ratio output transfer function, or this Dewey ratio, not control. It's the same. Okay, control is only Dewey ratio to output, and the control to output is the same, except the DC gain, FM modulator gain is coming in. But this one is Dewey ratio actually. It really doesn't matter, but this is Dewey ratio. Dewey ratio to output transfer function. So this is the CCM case. You know this is 20 log Vs, and this is double pole frequency, power state double pole frequency, and the slope here is -2, -40 dB per decade, and somewhere there is a ESR, omega ESR, then this, oh no, -2, okay? So this is -2, and this is -1, right? So this is the case of the CCM, okay? Phase is 0 here, and phase goes to this transition over this double pole frequency, and at this frequency, it becomes -90 degree, okay? So phase here is -180, -180 degree, okay? This is the CCM case, okay? The difference between CCM and the DCM, everything is the same, the compensation is the same, and all the parameters the same, only this R, load resistance, is increased or not. So, okay. So with a large load resistance, then this large resistance R is generating a substantial damping, okay? In DCM operation, usually the quality factor of this double frequency in CCM is this number, 2 or 5, some number in between, okay, can be larger than this. That is a special case, but usually something in between is okay. Okay, this means this if Q is larger than 0.5, you have double pole. Okay, two complex conjugate pole. Okay, but if with sufficient damping due to this large resistance, Q decreased smaller than half, less than 0.5, then this double pole splits into two dual poles, and one goes to low frequency, the other one goes to higher frequency. That is shown here. So omega P1 goes this direction, and the other pole is going this direction. Okay. Actually, the distance between this and this should be the same. Okay. You can prove that, and maybe okay. Let me move this. Assume this omega ESR is occurring at higher frequency. Okay, so this is omega ESR. Then we have omega ESR here, and this will be something like this. Okay, and phase here is 0. Here at low frequency is 0, but in this region, phase is -90 degree. The slope of this magnitude is -1 and phase is -90 degree. Okay, so it remains this minus degree up to this frequency because you have this continuous slope of -1. Okay, so this is the characteristic behavior of converter in DCM operation. I wrote down here. Okay, so this first I explained this. Due to this logic Q, substantial damping is provided, generated, and Q becomes smaller than 0.5. Then the double pole omega naught will split into two real poles. One is at low frequency, and the other one is very high frequency. Okay, so the result is this, right? This summarizes the characteristic of this and this curve. So you have -1 slope. This is the first order characteristics. There is only single pole up to this frequency band. Okay, so for first order system, like dynamics. This is not a first order system. There is some another pole is coming later, but in this region, characteristics are very similar to those of first order system. So first order system like dynamics. Okay, and more important thing is this pole is occurring at very low frequency. It's called dominant pole. Dominant low frequency pole. At this one, omega P1 becomes the single dominant low frequency pole. This will dominate the dynamics of this power stage dynamics of this converter, buck converter. Okay, and the midband gain of this Yuri ratio to output transfer function has been reduced a lot because of this pole. So this much of area is lost here. Okay, so this is the reduction in the midband gain. So let me show this. So this will affect the dynamic closed loop dynamics of this converter. So this again same graph. Okay, but think about the characteristic of converter dynamics in CCM and DCM. Which one is worse? Of course, the CCM characteristics are worse because this was problem. Okay, the original problem comes from this -180 degree phase delay occurring at the double pole frequency of low pass filter in the power stage. That was the origin of the problem. This -2 slope or -180 degree was the problem. So to fix this problem, we employed two zeros around the double pole frequency. So this is the worst and this is the good. Okay, so this is -1 slope and phase remains this -90 degree plateau for long frequency range. So this is better. Okay, so when you are designing the feedback compensation, you should consider the worst characteristic, worst case. Okay, so if you design your compensation using these worst characteristics, if converter is stable in CCM operation, then converter will be also stable in DCM operation. Okay, that is the reason why we are not worrying about the DCM. Okay, much. We are worrying about CCM, and we design the compensation assuming this CCM. That is the actually proper approach. That is the good engineering approach because this is the worst case. So we use the compensation design for the worst case. Then the converter becomes stable if converter moves in the DCM operation because this dynamics in DCM is better than this CCM case. So we use the worst case for the compensation design. That is written here. So CCM transfer function present the worst power dynamics. So you should use this one for the compensation design. Then the resulting design will guarantee stability for both CCM and DCM operation. Okay, so looks okay, sounds good, but there is a very serious problem here. Let's take a look at the loop gain characteristics. Okay, compensation is designed. We use the previous compensation designed for the CCM operation. So I'm comparing this loop gain characteristic. So R of 2 ohm, 1 ohm, 0.5 ohm, they are all CCM. Okay, so CCM shows this, and the crossover frequency is the same regardless of change in this R values. When converter is CCM, they are very similar, and the phase margin is this one, and this is more than necessary. Minus 180 is somewhere here, so we have sufficient phase margin. Is stable. Okay, and load resistance is increased and converter moved in the DCM operation, then loop gain characteristic is shown here. Okay, so this is the case. This is the DCM. This is the deep DCM, and this is the deeper DCM. So converter is entering deeply in the DCM operation. Then loop gain changes in this manner. Okay, there is some change in the loop gain crossover frequency. But if you take a look at the phase margin, okay, then phase margin is some case larger than this one. Okay, phase margin is distance between here to minus 180, and this one is slightly larger. This one is larger. This one is slightly smaller. Okay, so for some case the DCM operation becomes more stable than CCM counterpart. Okay, there are maybe four problems here. First one is loop gain crossover frequency is reduced a lot. Okay, for the DCM case, loop gain crossover frequency was here, and it occurs much lower frequency in DCM. So reduction in omega C, this create delay in response time. So we'll see that later. So the result of this change is slower response compared to the CCM case. Response becomes slower. Okay, and the magnitude of the TM is reduced this much. Okay, the area is the additional benefit, attenuation in closed loop transfer function due to the feedback loop. Okay, that benefit is reduced this much, right? So reduction in magnitude of the TM will generate reduced attenuation, but somehow the phase margin becomes larger. Okay, loop gain crossover frequency is narrower, but phase margin becomes larger. So maybe sometimes it becomes more stable in some sense. Okay, all right. One additional comment here. So somehow, if you take a look at the loop gain characteristics by combining the control to output transfer function, duty ratio to output transfer function, and what loop gain in the DCM operation, if we merge them together, okay, no, the feedback compensation. Okay, let me take my word back. Okay, combine the characteristic of control to output transfer function and the feedback compensation, then you have one dominant pole at low frequency. Okay, and no zero, another zero is coming later. So because of that, this region, the slope is -2. Okay, and the phase is around -180. Okay, less than that, but if there is nothing after this, it will go to -180. Okay, and this area is flat. Okay, phase becomes slope becomes 0. Okay, slope becomes 0, and the phase will climb up to 0 degree if nothing is here, but there is some pole. So this is something like this, right? So there is a two increase in magnitude slope by 2. Okay, and here this phase is increased around 180 degree. Okay, there is a double 0 somewhere here. Okay, so you can predict this based on this shape of this magnitude curve and the phase curve. Okay, or you can consider the voltage feedback compensation and the duty ratio to output transfer function in DCM operation, then you can conclude the same thing. Okay. So in area A is around this loop gain crossbar frequency. In DCM operation, there is a double zero in TM. Okay. Because okay, the loop gain has double zero because of these characteristics. That means closed loop transfer function will have double pole around this loop gain crossover frequency. Why is that? For example, this is the output impedance. Closed loop output impedance is open loop load current to output transfer function divided by 1 plus Tm. Okay, so we are ignoring 1 around this region. Then this is coming in the denominator. So it was double zero. Double zero is coming here. Then this becomes what? Double pole. Okay, so at this frequency, there should be a double pole. Double pole. This is, for example, this is a closed loop output impedance or closed loop input to output transfer function called audio susceptibility. Okay, so there is a double pole. Okay, so this is entirely different from the CCM dynamics. Okay, the reason I wrote here because this output impedance is determined by this is open loop, the same. Okay, and there is a loop gain which has double zero here is coming in the denominator. So this closed loop transfer function should have double pole at the loop gain crossover frequency of DCM converter. So that is due to this factor, the control design tailored means designed for the worst case CCM operation offers stability. Okay, converter remains stable. Sometimes it becomes even more stable than the case of CCM. Okay, then the problem here is this step load response is much worse than this one. Okay, let me explain this. So I'm comparing the closed loop output impedance of the CCM, this one, and CCM with this output impedance. It generates this step load response, which is extremely good, almost optimal. And this is the first pole frequency. It corresponds to the second compensation zero. So this is basically this is the first order system. So this is there is one exponential decay, and the initial value is determined by this k. Okay, some number you can calculate this if you want. This is actually ESR times the step change. Okay, then this is exponential decay with this term. So this time constant is 1 over this omega p, which is omega g2. So this is much faster. Okay, that is because of this. And CCM, this output impedance looks like this. Okay, so there are three difference compared with this one. First, this magnitude is very large. The maximum value was somewhere here. Maximum value was increased to this. Okay, so larger peak value is the first observation, and the second observation is this omega c. There is this peak. Okay, actually this is double pole. Slope, increasing slope is +1, and decreasing slope is -1. This means this is double pole. We predicted there should be a double pole around this based on this loop gain characteristics. So you are seeing double pole here. Okay, so double pole is occurring here. Some oscillatory behavior will come out, and this frequency is way lower than this. Okay, then transient response of this DCM for the relatively same magnitude of load current change. This one and this one. This one is significantly worse than this CCM case. Okay, there is oscillation, right? Okay, first this peak value is large. Then based on this observation, you infer, the larger the converter will experience larger deviation. Deviation is overshoot or undershoot in our voltage, which is true here. Okay, this is very small, this is very large, and because this is corner frequency, is occurs at higher frequency. This is also corner frequency, occurs at much lower frequency. Then and this is the pole. Okay, so this is this frequency. There is a sinusoidal oscillation, and this is the frequency of oscillation is this one, and there is some value, okay, exponentially decaying value, but this sinusoidal part is coming in, okay. So you ignore this part, okay. So this is the load change is occurring in this manner. This load current is decreased here and increased here. This is a variation of I/O, okay. If you removed this, then this response will go like this. It will generate this sinusoidal oscillation, okay? And the double pole sinusoidal oscillation frequency is this one, omega c. So because of presence of this double pole, the response becomes very slow. And we have double pole. Double pole is generating this. Okay, this term is determining this one. Is decaying slope of this sinusoidal wave, but there is oscillation. So with this presence of the double zero, not double pole. It was double pole, but it becomes double zero. In output impedance is generating some okay. That is proved here. Right. The period of this oscillation, so oscillation period is this one. Okay. So this is 2 pi divided by omega c, which is loop gain crossover frequency. So using this, maybe you can predict this, and everything can be determined using the knowledge about linear time invariant system. Again, this is the benefit of using small signal model. So without small signal model, this analysis is groundless. There is no theoretical background for this. Okay, but you can do everything. Okay, so the control designed for the CCM produce limited performance. Limited means volts performance in DCM operation. Okay, this always occurs when CCM, DCM transition, if you use voltage mode control. If you use the current mode control, they generate very similar dynamics. Okay? DCM response will be very similar to this if you use current mode control. There is another reason why using current mode control. So basically, this is the end of voltage mode control. You covered many things. Okay? Maybe this is the tedious. Okay? In the most textbook, they skip this, or they have a few couple of pages with this. But I spent some time, okay, effort to explain this. But understanding this is very important to understand the current mode control properly. Okay, so you have there is a limitation. Voltage mode control is only applicable to buck converter, okay? And even in the buck converter, it generates very volts dynamics when buck converter moves into DCM operation. Okay, that is problem. Okay, so they developed alternative control scheme called current mode control. Okay. This is the schematic diagram of current mode control. So without this is a lamp, okay? Assume this is gone. The blue curve is something additional. Without this is the voltage mode control. Okay, so voltage mode control, the prime object is to regulate output voltage. That is the same in the current mode control. Okay, you want to have the stable voltage source, then output should be regulated. That aim remains the same. Okay, so output is regulated in this voltage mode control and current mode control. Okay, difference between voltage mode control and current mode control is shown here. But first, take a look at the voltage mode control. There is one single feedback path from the output voltage. This is necessary. We want to regulate this voltage, so we should sense this. Then this goes to this PWM block, and V ramp is going to this block to perform the PWM scheme. Okay, so single feedback pass from the output voltage, but this one is shielded for only buck converter only. If you really want to emphasize something, you put only in the rest. Okay, so I'm strongly emphasizing this only buck converter only, and in DCM performance becomes worse than CCM case. We have seen this this fact in the previous lecture slide. Okay, so alternative way of this is called current mode control, and the only difference is this one. In current mode control, you sense this inductor current. This is the symbol of the current sensor. This circle is just the symbol. This means the current information is coming into this, and there is a block, some simple block called current sensing network. This circuit is sensing the current passing through the inductor. This can be a simple resistor for some case. Okay, this should be a resistive parameter because the dimension is current here and dimension here is voltage. Okay, so this should be resistive component, and we add them together, RAM and VI coming from this current waveform added together, and the control voltage is coming out of this voltage feedback loop, and the PWM is performed using these waveforms and these waveforms, actually using 3 waveforms. Okay, that scheme is called current mode control. Okay, so there is additional feedback from the inductor current on the top of the existing output voltage feedback. Okay, you are not trying to control the current. The name can be confuse you. You are not controlling current at all. You are controlling output voltage. Because of this should be the voltage source. Okay, you are using this additional information from the inductor current to assist, to have some benefit of this additional feedback. Okay, so this is the name, current mode control. Can confuse some people. Okay, we are not trying to control the inductor. We are not interested in this inductor current. We are only interested in output voltage. Okay. So current mode control. With this control scheme is applicable to all PWM converters. Okay, even this structure of this voltage feedback compensation becomes smaller than the case of the current mode control. Easier to design. Okay, and with this control, the performance of the converter in CCM and the DCM, they are almost identical. Right. So this is very good control scheme, and this current mode control is most important topic, okay, in PWM power conversion technique. Okay, so this is the end of topic 9-2. Okay, so we are closing this argument, but I want to emphasize one very important fact. Okay, so now this voltage mode control is used very limited manner. Okay, very few people they use voltage mode control for the buck converter or buck derived converters only. Still, this is useful. There are some people is using. If people they are afraid of using the current mode control because they don't know the details about the current mode control, they still use voltage mode control for the buck converter. Okay, but most of people they are using current mode control because current mode control is good both for converter and other converters. It's good for all converters, all right? And it provides almost consistent performance in CCM and DCM. Okay? Maybe you think I don't care about the current mode control and I'll study. No. I'll ignore all the story about the voltage mode control and I'll study current mode control only. That is the very bad idea. Okay, wrong idea. Most important thing is the knowledge you obtained through these discussions, previous 10 lectures, is extremely important. Even you are dealing with the current mode control. Without that knowledge, you cannot understand the current mode control. Okay? So this voltage mode control is extremely important. I think I explained the reason for this several times because in the past, there is only one control scheme, voltage mode control, and they used this and they developed a theory about this kind of story using voltage mode control. Okay? All right, so this is the end of this lecture and end of this topic. Okay?